a real pleasure to talk about this topic here. And I just want to mention that this really is only a part of the research I do. Most of the research in my group is actually more on trying to understand what we have unintentionally done to the atmosphere, how human behavior is changing chemical processes in the atmosphere. The other thing I want to say as we go through this talk is that I'm actually not a climate scientist per se, I'm an atmospheric chemist. But there's a component where atmospheric chemistry, of course, is part of the larger climate picture. And what I show you here, if you look at this picture, I don't know how well you can see it from the back, was a cartoon that I actually originally made when I presented about this in another mountain area in Austria, where I also gave a talk. And it's sort of a little bit of it's meant a little bit controversial, but that what it's supposed to show is that if we go as business as usual, the world heats up. That's why the skier is looking and there's no snow for him to ski. This is obviously just a cartoon. And we have a certain amount of ozone in the stratosphere that protects us from UV radiation. Then there are geoengineering scenarios where we're keeping CO2 the same. This is the cause of climate change. We're not attacking this. What we're doing is we're putting what we call sulfate aerosol in the stratosphere, and that cools down the planet and the skier can ski, but there's less ozone, and the temperature of the stratosphere, that's the part of the atmosphere that's higher up, actually is higher, and you can see that the skier has a red head because he's getting a sunburn because there's more UV radiation. And then what I'm interested in as a scientist is the question, and this is just one of the side effects that we know if we try to use this method. And then on the right-hand side, there's this question of whether there are new materials other than the ones we've thought about, that can cool down the planet and allow us to ski, for example, but at the same time don't reduce ozone so that you don't get a sunburn. And obviously this is just a cartoon, but it sort of exemplifies this question that I want to get into. Before we get into this, I sort of want to point out that this is of course not just my work. There's a group of people that I'm working together very directly. David Keith in particular is really one of the people at the forefront of thinking about this solar geoengineering, and he's one of my colleagues. And these are other people I'm working with on this. So, if we look at the background for this, I want to get a little bit into this climate change question. We are living in a changing world. We have rising temperatures that sort of are this is sort of the global land-ocean temperature index, where you can see sort of a discrepancy in Celsius, where since 1880s temperatures have sort of been creeping up. And we're also in a world where the global sea levels are changing. And there are a lot of other impacts. So we know the world around us is changing. And another example for this is, for example, that we have coral reef bleaching. And there's been a lot of news, for example, about the Great Barrier Reef and loss of coral bleaching in the Great Barrier Reef. And we also have more extreme events. This shows sort of where India in 2015 was hit by a very severe heat wave that actually also killed a lot of people, resulted in droughts, had lots of impact on agriculture and generally sort of on ecosystems and humans living there. And probably also in this area of the country, you're quite familiar that droughts are happening. And whether any individual drought itself is tied to climate change or not is a different question. But if you look at the climate models, you do expect to get more extreme events. You expect things like coral reef bleaching. This idea with the hurricanes, whether you get high intensity hurricanes, is actually, that's why I have a question mark here. That's not so clear. And a lot of these questions aren't quite clear, but you definitely can expect to see a lot of change. And this change has impacts on ecosystems and humans. And what do we know about what is contributing to this longer term change? Not necessarily an individual event, but the longer term changes. And a lot of that has to do with emissions of carbon dioxide. The fact that carbon dioxide, it is a greenhouse gas, the fact that in effect has to be warming up the planet is in a sense very trivial. There's no question about this. What really happens in each region is a much harder question. And another thing I want to make clear is the scale of the problem we're facing. If you look at the rate of CO2 addition, and if we believe CO2 is a cause for this, what you see on the left-hand side is an ice core record from Antarctica, and this is the CO2 mixing ratio that you get from the ice. And if you look at one of the sharpest rises that you see in this ice core record, which is shown here, it happens over a scale of about something like 5,000 to 6,000 years, and CO2 goes up by a certain amount. And if you calculate that, this is one of the fastest rises of CO2 that we have a record on in the paleo record. It goes up by 0.01 parts per million. This is the amount in air. 1 part per million is 1 molecule out of a million molecules. It goes up by 0.01 ppm per year. If we look at the recent record, And what you see with the CO2 rise there, you see that the increase of that, this is from about 1960 until 2017, 2015 actually, sorry, you can see that the rise is about 1.8 ppm per year. This is orders of magnitude faster than what you can find in the sort of paleoclimatological records. So we are changing CO2 in the atmosphere on a rate that has not been previously observed to our knowledge. And we believe CO2, and one of the things that's important is CO2, we believe, is one of the causes of climate change. If we look at what that looks at, and this will become important on the next slide as well, we can sort of look at global emissions of CO2, and this is in gigatons CO2 per year. And you can see that some of it comes from changing land use and forestry, and there's a lot of this gray segment which comes sort of from human activity, that's fossil fuels and other components. And I just want you to remember this number is sort of at the moment, if you go here, close to something like 40 gigatons of CO2 a year, not quite, but in that area. And then depending where you cut from, you can look in how different areas are doing this. And sort of there's a big difference, for example, between France and Germany, even though those are both in Europe, it's nearly a factor of 2 difference in the amount of CO2 emissions per year per capita. So this 40 gigatons of CO2 I want you to remember, and we're sort of, up to now what we've done is probably a little less than 2,000 gigatons of CO2 cumulative emissions. And now I want to get to sort of what the IPCC, this International Panel for Climate Change, says, well, we need to address this meeting. There was this meeting in Paris. So they set out these goals. We want to keep temperatures definitely below 2 degrees Celsius, and if we can, we want to keep them below 1.5 degrees Celsius above pre-industrial temperatures, right? And one of the issues with this IPCC scenario of 1.5 degrees Celsius is when you look at this. So what they do is they run a large number of simulations, and what you can see here is that if we want to stay below 1.5 degrees Celsius with a 66% chance, that means, in their language, 66% of the models stay below this number at the end of the century, that altogether you can emit 2,250 gigatons of CO2, which meant in 2011 there were 400 gigatons of CO2 left to emit. And now if you can do math and do 400 divided by 40, that's not a lot of years, and this was in 2011, and that means that in something like 2020-something, we would have to cut CO2 emissions to absolutely zero to actually get to that scenario without some other measures that you have to bring into action. Now, there are a lot of different scenarios to do this, but this shows that this 1.5 degrees Celsius in the current world and in the trajectory for CO2 emissions, which at the moment does not show a big sign of going down, really is just, and people may disagree with that, and they can say that, but I just think that this is just not achievable. It is not realistic to have this out there. And even 2 degrees Celsius, you can have more emissions, but it is still a limited amount. So we really need to think about what solutions we can have to approach this. And fundamentally, there are 3 things we can do for climate change, right? One is we can reduce emissions. That is something we will have to do in any case, in my opinion. Without emission reductions, there's really no way forward, and that's called mitigation. We can also adapt to climate change, and that is also something that I believe will have to happen, and also that has happened over the ages of humanity. It's just that if that rate of change is very fast, it is hard to adapt. And so this sort of supposed to be the picture for mitigation. These are some of these giant floodgates that they have in the Netherlands to adapt for. In that case, this is just for floods, but you can imagine cities on the East Coast are talking about trying to build these things in case sea levels rise more and you get more storms coming in. And then there's this, and these 2, I think most people would admit we have to do both of those. And if you look at the climate change debate about 20 years ago, people said you really shouldn't be talking about adaptation, but because if you mention adaptation, people will think, oh, that means I can keep emitting, we'll just adapt. And so it was a taboo word that you couldn't use. Geoengineering is this 3rd thing, and that is an active intervention in the climate system. And that, of course, is very scary, because we know how often human things think that we know what we're doing. We'll fix this problem, and then something else happens. And there's fundamentally two different ways, as Judy said. There's carbon dioxide removal, and this is sort of a not real, this is a fake picture of what a plant that actually is going up in Squamish at the moment in Canada to get CO2 out of the atmosphere. In this case, they want to turn it into fuels that you can use. And you can remove carbon dioxide, or you can modify the albedo. That is the reflectivity of the planet. If you make the planet brighter, more sunlight gets reflected back into space. Right? And these are the two types of geoengineering or climate engineering that are starting to be discussed. And I want to point out these are very different things. For this carbon dioxide removal, there are a number of ways that you can do this. You can do direct CO2 air capture, for example, where you get CO2 of the air, you put it down into the ground and hopefully store it for a long time. You can try to manipulate ecosystems so that you have more forests taking CO2 out, perhaps turn them essentially back into coal and store the coal in the ground. And there's also ideas of putting iron into the ocean, a number of other ideas. The important thing is that this actually addresses the cause of the problem. If we believe CO2 is a large part of the climate problem, if you take CO2 of the atmosphere, that actually addresses the cause of the problem, right? However, it is slow and probably very expensive, right? And so this is a big problem from an economic point of view. Then there is the solar radiation management, and there's a number of different ways you can do this. I haven't listed all of them. People have talked about putting mirrors in space where you can reflect back some of the sunlight and you can tilt them to vary that. You can try to change the properties of clouds, especially of the oceans, to if you have more reflective clouds, more clouds that will reflect sunlight back into space. And one of the other ways that you can do is you can actually put aerosols that are small particles up into the stratosphere, say at 20 kilometers, that also reflect sunlight back into space. Now, the thing that makes this dangerously appealing this is pretty fast and cheap. This is something that one fundamentally could implement fairly quickly at a low cost, but it's also imperfect and highly uncertain what the side effects are. You are not addressing the cause of this. You're doing nothing to CO2. So things like the ocean getting more acidic because there's more CO2 in the atmosphere, no impact. So this actually fundamentally is different in that you don't address the cause. But why would you then even consider something that actually doesn't fix the problem? And that is where that's why I like using this painkiller analogy, in that there are times where probably most people in the audience here have taken painkillers. And in most cases, those painkillers don't actually fix the problem that you're having. And they can do all kinds of bad things because you don't notice the pain, right? Like I have herniated discs in my neck, and when I take my painkillers, it doesn't hurt anymore, but I may be doing things I shouldn't be doing because I don't notice the pain. But why could you do that? If the pain gets very big, as most of us know, there probably is a reason to take painkillers, right? And so the question is, could there be a point where suffering or ecosystem change gets so big that people say, well, we need to do this to buy us time to actually fix the problem, give us time to fix the actual problem. And the idea is that the risk of climate change is related to the rate of change, the idea of extreme events that occur that have a big toll, or that there are tipping points where suddenly the climate suddenly changes. And as I'm not a climate scientist, I don't really like talking about the last one because I don't understand that. But certainly slowing down the rate of change so we have more time to fix the problem or to adapt seems something that is reasonable, where you can imagine you have a high rate of change, and if you can use solar radiation to reduce the rate of change and sort of spread that out, that will give more time to adapt. Mitigation efforts, this idea of fixing this with CO2, as I think I've shown, doing that on the short term seems very challenging and hard. And so one of the ideas is to use solar radiation management to reduce the rate of change and sort of do something that people call peak shaving. So imagine, here's some climate risk. You do fossil fuels forever, that climate risk just gets crazy. As if you cut emissions to zero, it'll level off and go back down very slowly. And if you do other things like carbon removal, you can get this back down faster, but you have this peak. And so perhaps you can use solar geoengineering to sort of shave off how high that climate risk may get. And this is just a suggestion. I'm not saying this is actually what would happen. So what do we know about this? And now I'm getting closer to where my research goes, is that we have some natural experiments for this idea of injecting aerosols in the stratosphere, and that are large volcanic eruptions. And so the one that everybody uses is the Mount Pinatubo eruption that puts something around 10 million tons of sulfur into the stratosphere. right? So actually, it's not the ash you see here. It's a gas, sulfur dioxide, that goes all the way into the stratosphere with a volcano, and in the stratosphere turns into little particles that we call sulfate particles. In reality, they are concentrated sulfuric acid, and those are the things that reflect sunlight back. And so we have an experiment. Nature did this experiment for us, and if you look here, you can see that actually what happens, this temperature anomaly is just a deviation from what you would expect. You can see that in the troposphere where we live. There are observations and a model here, ignore all the different lines. But fundamentally, you can see that after Mount Pinatubo, which was here, you can see temperatures actually were lower where we live. And it makes sense. If I reflect back sunlight, less sunlight hits the surface, it gets cooler, right? So that fundamentally means that's great, let's just do it. We're cooling down the temperature. What could go wrong? And many things can go wrong. One thing you actually see is that actually the amount of water in the troposphere, how much water there is in the air, also goes down. You can see at the same time here, the water anomaly, you see a similar signature. So that means there's a potential that you're going to influence the hydrological cycle. And this is a complicated topic where the question is whether that's actually bad or good. So let's go on. What else happens? Other side effects. So after Mount Pinatubo, if you look at global mean ozone in the stratus, and especially looking at the stratospheric part, that's the part that protects us from UV radiation. And what you can see here is across sort of an annual average, there's sort of this blue envelope is the historical data from 1979 to 90, and you can see it has a certain range. And then you can see that in the years after Mount Pinatubo, and I have to say there were also additional volcanoes that contributed to this in certain regions, you can see that there was noticeably less ozone in the stratosphere. That means there's less protection from UV radiation, and you've got to think about, well, what is the impact of that, for example? And you have a decrease in stratospheric ozone. Another one that actually I'm more worried about is that what also happens, here's a temperature record across years. So from 1979 to 2000, you can see sort of a deviation of the temperature in degrees Celsius, and the numbers per se don't really matter, so don't worry in the back if you can't see those little numbers. But what you see, there were two big volcanic eruptions, Chichon, and then here's Mount Pinatubo, and you can see the temperatures in the stratosphere rose significantly. Well, why does that matter? That means that the circulation in the stratosphere changes. The same way, if you put a pot of water on the stove and you start turning the heat on, and you can see how that water is starting to circulate differently, the same thing happens in the stratosphere. And all those things are not isolated from the rest of the planet. So all of these things have trickle-down effects, and you have these domino effects. So what you're doing is changing a number of things, and so there are numerous known consequences and risks, and there are also numerous probably unknown consequences and risks. And one of the things I want to talk about is what can we do as scientists to think about this? And I want to talk about where I think there is room to do science about this. And that is that first we actually need to understand. So we say, well, let's put aerosol in the stratosphere, that can cool down the planet. We first need to make sure we actually understand that stratospheric system. Right? If you want to perturb something, you better make sure you understand what you're perturbing. And there actually are a number of things. The stratosphere is fairly well understood, but there are a number of things we don't know that well yet about it. So what I've been telling you is that, what you put up there is sulfate aerosol. And that's very simple. It's sulfuric acid with a little bit of water. And there's actually been work that's shown that sort of on the left-hand side, and I apologize if this is a little complicated, where this in essence, it says ozone, but really this is altitude, so you can think of going up in the stratosphere. And the part that I've been talking about, that it's sulfate aerosol, this is a fraction of all particles. So here, this would be that 100% of all particles are that type. And the part that's actually sulfuric acid, without anything else in it, is here. It actually is never the dominant fraction of aerosol at latitudes in the lower stratosphere. In the lower part, you have all kinds of mixed organic sulfate particles. There's organic molecules, hydrocarbon, oxidized hydrocarbons in there. And as you go higher, you actually have that most sulfuric acid particles have a lot of meteoritic iron in there. So there's iron metal dissolved in this. Now, whether that matters or not, we don't really know yet. But it says that we don't really understand stratospheric aerosol yet, at least what we use in models. At the same time, we actually don't know whether we understand the stratospheric sulfur budget that well. So if we want to perturb that, it'd probably be good to understand that. And fundamentally what we have, if we use different methods of looking at this, we can use in situ observations from a plane to look how much SO2 goes in the stratosphere. We can use satellites to get the models to tell that. And then we can do estimates of total sulfur. They range from 3.6 times 10 to the 3 megatons of sulfur to 181 times 10 to the 3 megatons of sulfur. These are not exactly the same things. This has not just SO2, but these two are. So there's a huge variation in what we think is going on about the sulfur budget. And the problem is, of course, in a geoengineering scenario, you put, remember, 1 Pinatubo, 10 megatons. So that outweighs all of this. But if we don't understand the sulfur in the stratosphere, it's sort of, you've got to be careful in adding more of that. So we need to actually understand the actual atmosphere that we have right now better. And the other thing is that I think it's interesting, as a chemist, I am very interested in trying to think, well, it's great that nature puts sulfuric acid into the stratosphere. We understand that fairly well. But as a chemist, I think there's many, many different materials. And is there perhaps a material out there that has less side effects than sulfuric acid? Right? And fundamentally, it's sort of hard to imagine that sulfuric acid is per se the best material possible for this. But it is the one we know the most about. And so there's two things that sort of really start the side effects of sulfuric acid, and that is based on their physical and chemical properties of those molecules, sulfuric acid and water. And so the idea is, well, both the temperature and the ozone come from these chemical and physical properties. So, what I'm interested in, and it'd be nice if other scientists also start doing this, is to look for better materials that are not perhaps acidic, which the acidity drives some of the chemistry in the stratosphere, that don't absorb light. So the reason you're heating up the stratosphere is because the sulfuric acid absorbs radiation coming from the planet, and that means energy goes into the stratosphere, heats it up. Can we find materials that don't do this? And then we don't only need to think about these, which are the impact on the stratosphere, but we also need to think about when these materials come back down. That's also important to consider about, right? What happens as they fall through the troposphere down to the surface? Does it influence clouds? Does it influence the ecosystems where they actually precipitate? Does it influence humans that are living there? There's a vast array of side effects and things we need to think about. And so I'll just make some suggestions. This is fairly early on. And we can think about different types of materials to, in essence, replace Mount Pinatubo. And we can think about materials that are entirely unreactive and don't absorb any of that radiation. And the perfect material for that, I actually think, are diamonds. And yes, and that is the normal response, and I admit that's the first response, and it sounds like, that's ridiculously expensive. But if you think about, in the history of science, if you think about that, each of us in our pockets probably has like devices made from super highly purified silicon that does something. If you had asked people about that 100 years ago, they would have said that is entirely nuts. Nobody will ever have this. So in the end, having diamonds is an engineering problem, not a money problem. Right? You can already buy diamonds in like 200 nanometer size. But why diamonds? Diamonds don't absorb any radiation. They are perfect, and they are super unreactive. In fact, you can clean them in concentrated sulfuric acid to make their surfaces clean. So in that sense, they are great. What happens, however, in the stratosphere is that they'll slowly collide with naturally existing sulfate acid particles, and that will coat the outside of these with sulfate and still result in more sulfate surface area that destroys ozone. And you can see this in what I call a trade-off plot, where down here you in essence have the cooling effect. This is radiative forcing in watts per square meter. For the more scientifically inclined, this just means cooling. The further you go to the right, the more you cool. And this shows how much you're changing the global column of ozone in a specific model, the AR2D model. And it shows that if you use sulfuric acid, you get ozone depletion versus the radiative forcing. And then in green, I actually show alumina, just because it's in the figure. I'm not a big fan of that. But what you also see is that diamond does have significantly less ozone loss for the same amount of cooling. So fundamentally, that sounds like that could be an interesting material. But to me, one of the problems I have with this is, imagine you're living somewhere and you're putting in, 2 million tons per year of diamonds in a very small radius, that if they come back down to the planet, actually humans would inhale them. That doesn't sound like a very enticing scenario. So this problem with these highly unreactive materials is that we don't want them to be reactive in the stratosphere. At the same time, when we want them to the ground, it'd actually be kind of nice if they sort of just became part of nature again and didn't deposit. Perhaps not. Who knows? Perhaps it's fine to have those come down. But you need to think about all these different aspects. This stuff comes back down. And the opposite of unreactive is to say, well, we have this problem that we're coating these with sulfuric acid. That drives the ozone chemistry. How about we go the other extreme? From unreactive, we go to reactive. and highly reactive. And so one thing that we've been investigating, and I'll show that in a second, is have reactive non-absorbing aerosol, and that's limestone, calcium carbonate. From a human health perspective, per se, calcium carbonate is pretty benign. If it comes back down, it'll probably dissolve very rapidly. And it is highly reactive. So what's going to happen with this is that the acids in the stratosphere actually will react with this and potentially reduce the amount of ozone-destroying chemistry. And in fact, if we put this in a model, we can even in the model, as we put in more calcium carbonate, we can actually even increase ozone in the stratosphere. This is in a model based on reactions that we essentially guessed. There's been no work on actually studying these reactions under stratospheric conditions. But one of the ideas, the main point of it is to throw out that there are very different materials that have very different properties, and if more people start thinking about this, because I doubt highly that I'm going to be, that me alone is able to find that material that may be the ideal material, that there may be more possibilities. And one nice thing about both of these materials, calcium carbonate and diamond, is that they do not heat up the stratosphere in their unreacted form. And so what we don't know, we did this model and put it in there and published that, is we actually don't know how this reactive material ages in the stratosphere. It will certainly react, but what will it do? Will it actually turn into a material that's even worse than the diamond or the sulfuric acid would be? And so what we're doing right now is we're trying to convince other people to do experiments to determine the chemical reactivity, the optical properties, and this is where the science comes in, to understand what calcium carbonate actually would do in the stratosphere. And I also want to point out that just because ozone protects us from UV radiation, that doesn't mean it's a good thing to increase stratospheric ozone. Fundamentally, a material you would want would do as little perturbation of the system as possible, right? And so I just want to show, and I'm going to be finishing up in a second, that we have some students who are doing experiments to try to study. These are these 250 nanometer calcium carbonate particles you can buy. And we sort of have an experimental laboratory set up. These are exactly the things that were actually done many decades ago to study the chemistry that results in the polar ozone holes. And so, just to show, as it's science, I want to show a scientific experimental apparatus so we can introduce these gases that actually result in ozone destruction in the end, and we can have a part of the experiment that we try to use to simulate the stratosphere. We try to have the temperature of the stratosphere, the UV radiation of the stratosphere, and just try to simulate those conditions. And do laboratory experiments to actually tell us whether these ideas, are totally off, or whether perhaps it's worth pursuing doing more research on this. And so one thing I want to point out that I haven't talked about, so this is all about science, and one of my aspects of this that I think is that if you sort of recall this 1.5 degree scenario and how, to me, far-fetched this seems, that I have a big concern. People talk to me and say, Frank, you really shouldn't be doing research on this topic, because by doing research on this topic, by mentioning it to people like you, people will say, oh, there's alternative things we can do rather than addressing the cause of climate change. And it means that you guys will say, you know what, I'm going to burn more CO2 now. We can do this. It looks fine. It could also be the opposite, that you say there's a crazy person thinking about this, that is scaring my pants off, I'm going to buy an electric car right now. And I'm not saying electric cars are necessarily the solution. But fundamentally, the problem is that if we're going closer and closer to this 1.5 degree scenarios, there's also the possibility that at some point somebody will say, you know what, we know how we can cool down the planet, and this will definitely cool down the planet. Well, let's just do it, and it's actually surprisingly cheap. And so I think it's very important that we actually do research on this. But keep in mind that this thing will never be the solution to the climate change problem, right? We're not addressing the root cause of climate change. It really is like a painkiller. And I actually generally then talk about opioids and that they're like opioids. And I think that's actually a very apt comparison. It has lots of new and poorly understood risks. But I think it's important that we do research to actually understand some of these risks better. As a scientist, I'm never going to decide. It's not scientists that will decide whether mitigation happens or geoengineering happens. That's politics. But as a scientist, I think we can provide facts. And I think providing more facts on the risks or the efficiency of this solar engineering is something that actually is very important. And there's big concerns that by doing this, I'm using money that should be used for actually trying to reduce CO2, or how do you get CO2 out of the atmosphere? And there's also big concerns that by doing these little experiments, you're going to go down the slippery slope where you're starting to do larger and larger experiments, and suddenly you're sort of going into actually using this, right? And one of the interesting questions, again, which is political, but is sort of interesting to talk about, is I don't know how many of you at home have debates with your better half about what the temperature of the room is and who gets to set the thermostat. And I don't mean this is not to trivialize the problem, but in this scenario, who gets to set the thermostat, right? I mean, again, but that's political, that's not a scientific question. But all these things play a role in this. And then the very last thing, and then I'm done, I just want to put up this slide to point out that one has to be careful as a scientist and hubris. And this is how many people in the room, I'm probably those are many scientists, have heard of Thomas Midgley Jr.? All right. He is hopefully I'm not going to be like him for various reasons, as you'll see. So he invented the CFCs in the 1920s. He actually got a lot of prizes for inventing CFCs. These are the substances that result in ozone destruction and the ozone hole, right? And at the time they actually said they're so stable in essence that there could be nothing possibly going wrong with these substances. They're actually great because they allow us to replace ammonia in refrigerators, which is nasty and all these things. These are a perfect molecule. He actually is also the inventor of leaded gasoline. Now that one, in this one, I would argue he really couldn't know. The leaded gasoline gets a little, he also got a lot of awards from that. And he actually did, to show this, he actually did an experiment where he poured this substance that's lead over his hands and inhaled it to show how harmless it was. It actually turns out he got horribly sick from that. So he actually knew that this was not a good substance, right? But he still really pushed it. And these are two of his inventions. And a third invention of his is quite tragic. And that is that he actually contracted polio, couldn't really move. He designed a pulley mechanism to help him get out of bed. And he actually got strangulated on that mechanism and died. So he's just a very interesting example of thinking about being an inventor and thinking you know what you're doing. And I know it's somewhat humorous, but it's also sort of true. You've got to be careful about this. All right, now I'll end with this. And that's it. I'm done. Sorry.